were discussing about the properties of discrete time systems in the past few videos, and so far we learned about linearity, stability, invertibility, time invariance, and causality. In this video, we will see the last property, which is memory. We will see the definition first and then see some examples of systems with memory and without memory. So let's get started. First, we will see what are memoryless systems. A discrete time system is called memoryless if its output at any instant n depends only on the input sample at the same time. There should not be any dependence for the output on the past and future samples of the input. As an example, y of n equal to a into x of n is a memoryless system because the output at instance n depends only on the input x of n at the same instance n. Another memoryless system is y of n equal to n into x of n plus b into x cube n. Here also, the output y of n depends only on the inputs at the same instance n. If you see both these systems, there is no need to store any past inputs or outputs in order to compute the present output. That is, no memory of the past inputs or outputs are required. Therefore, memoryless systems cannot include any delay elements. Now, another term for a memoryless system is static system. Okay. Coming to memory systems, the output at instance n is also determined by the past inputs. For instance, if the system output at time n is determined by the input samples in the interval from n minus capital N to n, then the system is said to have a memory of duration capital N. If capital N lies in the range of 0 less than capital N less than infinity, then the system is said to have a finite memory. However, if capital N extends all the way to infinity, then the system is said to have infinite memory. Now, another term for memory system is dynamic system. Okay, let us now see some example systems and see if they are static or dynamic systems. The first system we have is y of n equal to 2 plus sine of n minus 1 into x of n. As you can see, the output at instance n is determined only by the input x of n at the same instance n. The output is not dependent on any past values of input. So, this is a memoryless system. Now, some of you might have doubt that since we have sine of n minus 1, isn't that a past value of n? So, isn't the output influenced by the past instance n minus 1? Well, that thought process is wrong. Here, sine of n minus 1 is just a coefficient, and coefficients can take any values. Our focus should only be on the input term x of n and not on the coefficients. Okay. Now let us see the second example. We have the system y of n equal to maximum of x of n, x of n minus 1, etc. to all the way to x of minus infinity. So, to find out the output at any instant, the system should also have the knowledge of all the past input to the system. Then only the system can figure out the output, which is the maximum value among them. Therefore, as the system output depends on past values, this is a dynamic system. Now the third system we have is y of n equal to x of minus n. Let us analyze the system. Setting n equal to 0, we have y of 0 equal to x of 0. So present output depends on present input here. Let us see what will be the output in the case of n equal to 1. We have y of 1 equal to x of minus 1. Here the output at n equal to 1 depends on the pass value of input at n equal to minus 1. So output depends on passed input. Therefore, this is also a dynamic system, or in other words, a memory system. Now I would like to give you a homework question. Check whether y of n equal to x of 2n is a static or dynamic system and comment the answers in the comment section. Now before ending, I would like to stress the point that for a given system to belong to a classification, it should possess a particular property, and the property must hold true for every possible input signal to the system. If a property holds for the system in case of some input signals but not for the others, then the system does not possess that property. Thus, a counterexample is sufficient to prove that a system does not possess a property. However, to prove that the system has some property, we must prove that this property holds true for every possible input signal. Okay, that's all for this lecture.